the picture we have been working is if you have a map from a manifold itself, you try to draw the graph of that mapping. That was the interesting idea, the diagonal. And you look at a graph like this, which we denoted by gamma bar. And the fixed points are exactly the intersections of that graph with the diagonal, as we saw. Indeed, if you are here, this point does not move, it has the same value. And we saw that the Lefschetz number, lambda of f, is simply defined to be the intersection number between the diagonal and the graph. This intersection number is counted plus or minus, add them all together. So you look at those intersections and assign them plus or minus and add them together. And Lefschetz fixed point theorem was the almost obvious statement that if this number, Lefschetz number, is non-zero, then there must exist fixed points. Obvious, because if there are no fixed points, then Lefschetz number is 0. So that's what we had yesterday. Now, it would be nice in practice, and bless you, to be able to calculate Lefschetz numbers of various maps. What I mean by calculate? Well, usually in many applications, such a mapping is given by formulas. Yeah, suppose that you have a formula. We already saw one example yesterday, an important one, which took a point in the plane to the point in the plane. Can you calculate, is there an algorithm for calculating Lefschetz number? And the answer is yes. So I'd like to begin by stating that formula and proving it. This uses a little linear algebra, so please be patient with me. Suppose that the map is given by coordinates, so locally specified, expressed by coordinates, in coordinates, as in the standard way, yeah, for the assignment of x1 through xn, you have the first component of the map. If you like, this is y equals something like this. And then there are m components because I'm mapping an m-dimensional manifold to an n-dimensional manifold. Yeah. Suppose that you have an expression of f like this, explicit expression. Then it turns out that the Lefschetz number can be calculated explicitly also, the Lefschetz number of f. You remember what this letter is? Capital lambda, that's right, is equal to the sum over all the fixed points of the function. So you have to find the fixed points still, unfortunately, but you will see how this simplifies in practice. And then you calculate the determinant, you have guessed because it has to do with orientation, of the following quantity. F prime minus I. And this f prime is calculated at x minus I. So that's the x, and that's where the x appears. What is this I? Well, you can guess. That is the identity matrix. What's the size of this identity matrix, you think? M by M, exactly. M by M identity matrix. 1 along the diagonal, 0 off diagonal. And this is because this derivative is also an M by M matrix. Do you remember? We discussed this with various people yesterday, in particular Audrey. Where is she today? She's not sitting here. So you use the Jacobian. You take the partial derivatives of the first component, partial derivatives, and then you arrange them in a matrix, and that's what it is. So if you calculate this sign, you get the Lefschetz number. In order to convince you that this does have a chance of being correct, let's draw a picture when m equals 1. In one-dimensional case, the picture is easy to draw. This is m, and that's diagonal. And then there is a graph which might look like this. Okay. Often, this kind of picture, you are beginning to understand, is an abstract, symbolic, metaphorical picture. It's like modern art, if you like. It represents a situation in a suggestive way to us so that we understand, but usually such a picture is not a literal picture. When I, for example, draw a curve like that, I don't really mean that the graph is a curve. Sometimes the graph might be a surface, and so on. But in 1D, one-dimensional case, this is literally true. What you're seeing is actually true. So the diagonal is a straight line at 45 degrees, and the graph is this curve. So in a situation like this, according to the standard orientation that we took in the convention number 1 yesterday, well, the diagonal is oriented like this, the curve or the graph is oriented like this, and the ambient orientation is like this. So here, the sign is plus at that point. This corresponds, in terms of the derivative, to the statement that at this point, x minus, what is the 1 by 1 identity matrix? It's just 1, is positive. And that's true. The derivatives, the slope is larger than 1. And similarly, you have guessed already what's going to happen. The corresponding picture for the negative case looks like that. Here, if you look at the picture, it's negative because delta, the diagonal, and the graph are like this, 1, 2, and that's the opposite orientation to the ambient orientation. So this corresponds to the derivative at this point, the fixed point, being less than 1, that is that. And because the determinant in the 1 by 1 case is just a number, this illustrates the formula that we have to prove. This formula then, at least in one-dimensional case, seems plausible. Plausible means that we cannot yet check it, but it's believable. It seems to be true. That's what plausible means. Okay. Let's now prove it. As I say, we need a bit of linear algebra. Bless you again. Suppose that we write E1 through EM as usual, the orientation basis for M. What I really mean is that there's a local frame, and then those vectors define the orientation for that local chart, but that's good enough. Now, in order to simplify the calculation a little, we shall introduce a new notation. Each of these is a vector. It's sort of a long thing like this with 1, 2, 3, m components. You can see that, right? And there are m of them. So we're going to put those vectors, 1, first vector, 2 vector, and so on, all the way to the mth vector, put them together in a box and regard it as a matrix. In other words, in this matrix, the first column, as we call it, is E1, and then second column and so on, and then the mth column is EM. I hope this notation is clear. And we shall denote this matrix that we get by putting together as columns all those basis vectors, orienting basis, as E. Yeah? Okay, that's the matrix, E. And so E is m by m matrix. Now, let's write down then what the orientations are for delta, gamma, and the ambient space, ambient product space. Here is what they look like in explicit formulas. These induced orientations, as defined yesterday, are as follows. This was the convention 1 from yesterday. For delta m, what are the basis vectors that define the orientation? If you calm down, not panic, and think about it, it's simply this. Are you calm and not panicking? The delta, basis for delta, was the long vector of 2m components where you copy E1 and then directly underneath E1. Second vector is E2, directly underneath E2, and so on. So this is what the basis for delta m. To be precise, the first column, second column, third column, and so on, all the way to the mth columns, define the basis for delta m. Okay? And for gamma, is anybody imaginative enough to tell me what this is? You remember for gamma, the basis was E1, and underneath we had the derivative of f applied to E1. In the second column, E2 derivative of f applied to E2, and so on. So what do you think the basis will look like in terms of the matrix? E, and underneath f prime and derivative applied to E. That's all there is. And if you look at the first, second, third columns and so on, you see the orienting basis. I'd like to remind you that this f prime is a matrix, m by n matrix, what is called the Jacobian. Okay? And finally, for the ambient space, m plus m, it is easy. E, and underneath it's 0, because the defining basis starts with E1 and 0 underneath, E2, 0 underneath. At some point, you get EM and 0. The next vector is 0, 0, 0, 0, E1, and so on. So the basis looks like this. So that's a 2m by 2m matrix. And this 0 naturally represents m by m 0 matrix. Yeah, so it's a big list of zeros. Okay. Well, let's suppose that x is a fixed point. Okay? And I'm going to be slightly loose in my language. Each fixed point, and let's think of a fixed point as a point with coordinates x and x, the same coordinates. So I'm going to write it as this intersect gamma f. Okay, each fixed point, we must decide whether it has a sign plus or minus 1. So, contributes, let's decide which one it is depending on those quantities. Plus 1 or minus 1, accordingly as the following conditions hold. The condition for plus 1 is that the orientation defined by this and this matches the orientation defined by this. Okay? So that means that if you calculate a determinant consisting of this and this, and that is determinant of E and E f prime times E, that's a 2m by 2m matrix and determinant, and the determinant of that, the ambient, they have the matching or the same orientation if those two determinants have the same sign, plus plus or minus minus. They have the mismatched or opposite orientations if those determinants have the opposite signs, plus minus or minus plus. So all we have to worry about is the signs of those determinants. Note that the value, the magnitude of those determinants is irrelevant. You see, because if you have a vector like this, 1, 2, that's positive. If I have a vector like this and like this, the determinant will be much larger, but it's still plus. It doesn't matter the size, but what matters is the sign. Sign rather than size. So accordingly as whether those two determinants have the same sign or the opposite sign. Same or the opposite signs. Thus, we are reduced to computing the determinants. So please remember that this is the orientation basis for the diagonal. This part is the orientation basis for gamma, and this whole thing is the orientation basis for m cross n. Okay? I shall come over here. Now, how shall we decide whether they have the same sign or not? Here is how. Look at the first determinant, and we shall try to manipulate this determinant, transform it, so as to make it look like this determinant. So, what we start with is this determinant. Now, you have learned, I presume, a long time ago, how to do things to a determinant in order to calculate it, how to do things that don't change the value of the determinant. Do you remember, for example, that you can take the first column and add it to the second column, but that doesn't change the determinant, or take some rows and add them or subtract them from some rows and it doesn't change, and so on. Geometrically speaking, by the way, you are shearing the volume. That's a side remark. So let's calculate it like this. I'm going to think of it as those 4 boxes. And what I shall do is to take these rows, whomp, away from those rows. Is that clear? So I take the first row from the n plus first row, second row from the n plus second row, and so on, and nth row, the bottom of this top part, from the 2mth row, the bottom of the lower half. And what's going to happen? No, sorry, that's not what I'm going to do. In fact, I could have done it too, but okay, let's do it like this. So then, e minus e, I get 0. And here, I get e. And here, I get f prime of e minus e. That's what I get, right? Okay. But now, please remember that this is a box, m by m, and this is m by m, and that's a big 0. So if you calculate the determinant of this, it is simply equal to the determinant of e, which corresponds to that, times the determinant of this box. It doesn't matter what this is. I can do a little better. You see, this is equal to, inside this second determinant, is f prime minus the identity times e. And determinant is multiplicative. If you have the determinant of AB, it's the same as determinant of A times determinant of B. So this is equal to determinant of E squared, I can take it out, times determinant of F prime minus the identity matrix, on the one hand. On the other hand, determinant, which defines the orientation for the ambient space, the other determinant, is E 0, 0, E to begin with, so that's straightforward. It is equal to the determinant of E squared. Compare these two things. Determinant of E squared, because it's square of a scalar, some number, it's always positive. That's always positive. So these two things will have the same sign or the opposite sign, depending on whether this is a plus minus 1. And that's exactly the sign being contributed, you see, in the formula. That's the end of the proof. So the sign of determinant of f prime minus I is the size plus or minus 1, as advertised. I hope this is clear. If you like linear algebra, and if you think it's an easy and useful tool, I hope that you all will do, because it is useful and easy tool, then you like this proof. If you don't feel that way, well, I hope that you feel that way one day soon. But if you don't feel that way today, either because you haven't studied linear algebra thoroughly or because you haven't had enough coffee, then you can just accept this. Just remember how to calculate, and then we'll see a number of examples to show the formula in action. Let's begin with an old example from yesterday. Example 3, which we shall now revisit. Example 3 had the case of f, which was mapping from R2 to R2. I confess that in this situation, R2 is not a closed manifold. So Lefschetz ideology, Lefschetz philosophy, is not really applicable here because we are talking about the intersection number, and in order for the intersection number to be isotopy invariant, in order for it to be powerful, we have to have closeness. But we'll do the calculation to see how the calculation goes. It's an interesting example. Well, it maps the point xy to the point, as you recall, x squared minus y squared over 2 and xy. Those were the real and imaginary parts of half of z squared in disguise, as you saw. This has 2 fixed points. And those 2 fixed points have the xy coordinates as follows. 0, 0. Can you check that 0, 0 goes to 0, 0? I hope you can. Another fixed point. What do you think is the other fixed point is? What xy goes to the same point? In order to see this, it's nice to remember that this map is in fact, in complex notation, z goes to half of z squared. So 0 goes to 0. There's another point which goes to the same point. Which one is it? Banana? 2. Indeed, 2 goes to 2. In fact, 2 plus I0. So 2, 0 is another fixed point. Okay? And so those are the 2 fixed points, and we shall compute the signs at those points. At these fixed points, I'll continue over there. Sorry. At these fixed points, what is the determinant of this matrix? Oh, not this matrix, but that matrix. So f prime minus I. So in this case, f prime x, let's say xy minus I, this is a 2 by 2 matrix. When I say f prime, I mean again the Jacobian. This is equal to the following quantity. Do you remember what f prime was? We calculated this yesterday. It's x minus y, y, x. And then I have to subtract the identity matrix, which gives me this. And this, as you can see, is x minus 1 squared plus, interestingly, y squared. So this is always positive. If you want to be completely precise, at the point 0, 0, what is this? 0 minus 1 squared plus 0 squared, which is 1, that's positive. At the other fixed point 2, 0, what is this? 2 minus 1 squared plus 0 squared, that's again positive. So in either case, the sign is positive. So the Lefschetz number, unfortunately this number is not isotopy invariant because the manifold is not closed. But that's okay, we're just practicing calculation. This Lefschetz number is plus 1, plus 1. That's positive, so the sign is positive and positive is equal to plus 2. That's how you calculate. All right? You should recall that this makes sense because the equation really you're solving is half of z squared equals z squared, and it has 2 simple roots. B complex, they're both positive, z equals 0 and 2. That's really what's going on. Okay. That tells us how to compute the Lefschetz number in practice. Now, I will probably give you some exercises in which you can compute Lefschetz number by this brute force approach. And if needs be, you can program a computer to do this kind of thing. given an explicit formula representation of a map that you want to study. But from now on, in the main part of the course, we'll be using the idea and the picture of the Lefschetz number, Lefschetz fixed point theorem, rather than this formula. And we'll be deducing very striking results from just the idea and picture of Lefschetz. So we will not have so many occasions to use this formula. Nonetheless, this is a very useful thing to bear in mind.